Have you ever stopped to wonder what connects, say, the sweet, comforting smell of vanilla to the sharp spice of cinnamon? Well, today, we're diving into the amazing world of aldehydes, ketones, and carboxylic acids. These are the molecules that are, quite literally, the building blocks of our world. So just think about that for a moment. You've got the lovely aroma of vanilla, that warm, festive scent of cinnamon, and then the really sharp chemical smell of an industrial solvent. I mean, they couldn't be more different, right? But what if I told you they all share a secret chemical connection? Well, the secret is a very special family of organic compounds. It turns out all of these things are built from the same fundamental blueprint. We're talking about molecules like vanillin, which gives vanilla that delicious scent, cinnamaldehyde from cinnamon, and even something like acetone, a really common solvent. These molecules are like the invisible artists behind so many of the fragrances, plastics, and fabrics we use every single day. Okay, so here's our game plan for this explainer. First, we'll get into the chemistry behind all these familiar smells. Then we'll meet the real star of the show, the carbonyl group. After that, we'll look at its two main offshoots, aldehydes and ketones, and introduce their powerful cousin, carboxylic acid. And finally, we'll tie it all together and see why these molecules are so incredibly important. All right, let's get right to the heart of it all. The hero of our story is a small but really mighty structure, and it's called the carbonyl group.
So what exactly is this carbonyl group? You know, it's surprisingly simple. It's just one carbon atom connected to one oxygen atom by a double bond. That's it. This simple little arrangement, the C double bond O, is hands down one of the most important players in all of organic chemistry.
Now, the secret to the carbonyl group's power is something called polarity. You see, oxygen is a bit of an electron hog. It pulls the electrons in that double bond a little closer, giving itself a slight negative charge. And what does that do? It leaves the carbon atom feeling slightly positive, which basically paints a giant target on its back for other molecules to come and react with. This is the key to all of its amazing reactivity.
Okay, so from that one core building block, we get our first two major families of compounds, aldehydes and ketones. Let's take a look at how this one little structure can create so much diversity. And you know what? The difference between them is actually beautifully simple. In an aldehyde, that carbonyl carbon is always at the very end of a carbon chain, so it's attached to at least one hydrogen atom. But in a ketone, that same carbon is tucked away, kind of sandwiched right in the middle, between two other carbon atoms. Such a tiny difference in structure, but it leads to big differences in how they behave.
So how do they react? Well, the most common way is through a process called nucleophilic addition. Here's how it goes. First, a molecule that's rich in electrons attacks that slightly positive carbon we talked about. This attack forces the carbon to change its shape a bit, forming a temporary, kind of unstable structure. Finally, this structure just grabs a proton from someone nearby to become stable, and just like that, you've made a whole new molecule.
Now that we've met aldehydes and ketones, let's bring in another really important member of this chemical family.
So let's ask a new question. What do you think happens if our carbonyl group, instead of just bonding to carbons and hydrogens, gets attached directly to a hydroxyl group, an OH group?
Well, when that happens, you get something completely new, a carboxylic acid. When you put a carbonyl and a hydroxyl group on the very same carbon, they team up to form a new functional group called a carboxyl group, or negative COOH. And trust me, this changes everything. So what's the big deal about this new group? Well, it all comes down to one word, acidity. That hydrogen on the hydroxyl part is now much more willing to leave the molecule as a proton, an H+ ion. And the ability to donate a proton, well, that is the very definition of an acid. We actually measure acidity with something called pKa. All you need to remember is this: the lower the pKa number, the stronger the acid. So, for example, acetic acid, which is the acid in vinegar, has a pKa of 4.76. But then you look at something like trifluoroacetic acid, wow, with a pKa of just 0.23, it's a much stronger acid. It just goes to show how small tweaks to the molecule can have a huge impact on its properties. Okay, so we've covered a lot of chemistry, but what does it all mean for us, in the real world? Let's connect these molecules back to our everyday lives. Honestly, the impact of these compounds is absolutely immense. They are everywhere. They're used as flavorings in our food, as key ingredients in medicines, and as powerful solvents like acetone. But it doesn't stop there. They're the building blocks for adhesives, for paints, for perfumes, and for the plastics and fabrics that are literally woven into our modern lives. This quote from our source material really says it all, doesn't it?
carbonyl compounds aren't just some obscure topic. They are of utmost importance to the whole field. They are the chemical foundation for so many products that we all rely on, every single day.
So there you have it. We've seen how one simple structure, the carbonyl group, gives rise to this vast and vital family of molecules that really define our world, from its tastes and smells to its very materials. It really leaves us with a fascinating question. Knowing just how powerful and versatile it is, what do you think we will build with it next?